Today we are learning about non-conservative forces. So the past few classes we've been discussing work and conservative forces. And so non-conservative forces are those that do not conserve mechanical energy. So primarily in this class we'll be considering friction, but there's other examples such as air resistance that would fall into this category as well. Now, when we do problems involving non-conservative forces, we have to treat them as external work. We cannot define a potential energy for friction. So, as I've said before, in your problem solving, you'll probably want to define your system as broadly as possible so that you can use potential energy for gravity and for the springs. But when there's friction involved, you're going to have to calculate the work done by friction, at least for that one. Now, the other thing about non-conservative forces is that non-conservative forces depend on the path taken. So we know that the potential energy, all that matters is where you start and where you end, and not the path that you take. But here, for non-conservative forces, it'll depend on how far you go. Right? So if you take a longer path from point A to point B, you're going to experience more friction along that way. So if we look at this example, simple picture here of we have one person skiing and the other person trying to slide down the hill with shoes on grass. Now that may be possible if you've seen people try and in England try and chase wheels of cheese down a hill as they do for some sort of weird tradition. Definitely can get some sliding going on, but there's going to be a lot more friction and therefore a lot more energy lost from the system than there would be in the case of skis on snow, where the coefficient of friction would be very small. Now, we can calculate the work done by friction using our definition of friction, which is take the component of the force that's in the direction of the displacement, or in this case, opposite to the direction of the displacement, and multiply by the displacement. Now, you can see in my definition here for the work done by force, I've already gone ahead and put a negative sign, and we'll see why that's the case, that, that the work done by friction is always negative. Now, if we are doing our free body diagrams and we want to figure out the force of friction, we do it just the same as always. So you can see um, in the next equation, I've just substituted instead of force of friction, I've put in the coefficient of kinetic friction times the normal force, which is just the way we've always been calculating the force of friction. Now, if we look at this block, which is about to slide on this horizontal table, if it slides to the right, the force of friction is going to be to the left, and of course it'll be kinetic friction. So as that happens, we can see the displacement is to the right, but the force of friction is to the left. So if the force of friction points to the left and the displacement is to the right, they point in opposite directions, and therefore the work done is always going to be negative. So that's always true for friction. The work done by friction is always negative, and it's always going to remove energy from the system. Okay, now we're going to take a look at an animated example. Will allow us to look at conservation of energy, and then also looking at a situation where we have to apply work once we introduce friction. So if we start with the skater at a certain height, so we can see looking at the bar graph that all of her energy is potential energy, so the potential energy bar graph matches the total. And as we drop her into the ramp, we can see that when she's at the bottom, the kinetic energy becomes a maximum, then it goes back to potential energy. Oh, and I dropped her from a little too high, so she flies off. All right, so let's start that again, maybe a little bit more cautiously, so we can see it going back and forth, and I'll go back to normal speed instead of slow motion. Okay, so we can see the kinetic and potential, in this case gravitational potential energy, flipping back and forth, and we can see the speed going from a 0 when it's at the highest point, when the kinetic energy is equal to 0, so 0 speed here, and becoming a maximum at the lowest point when all of the energy is kinetic energy. We can also look at just a ramp where you drop in and then go off to straight line motion at the bottom. So we can see we start with all potential energy, and if we hit play, all that potential energy is going to become kinetic energy, and your speed just stays at that maximum value. Okay, but we know that this is only going to be true in idealized situations. So now let's go to a situation where we add in friction. So if we add in friction, so we'll start with like a medium mass and a medium coefficient of friction. Again, we'll look at the bar graph. Now, we know that throughout this, that friction is what we call a non-conservative force, meaning that it does not allow total mechanical energy to be conserved. Now, the way that this bar graph works is that, when you have friction, you're going to generate some heat, right? You can tell that by rubbing your hands together. The work done by friction there becomes the thermal energy or the heat that warms up your hands. So as we drop the skater in here, now instead of just going back and forth the same all the time, right, we still see kinetic energy increasing and then decreasing, potential energy going the other way, but the whole time we see this red bar creeping up. And that red bar creeping up is the work done by friction, which is now becoming thermal energy. So after a certain amount of time, and I'll let this go at normal speed now, normal playback speed, we can see that eventually all of that energy, it all started out as potential and is eventually going to become all thermal energy. We can also see this effect if we look at this kind of ramp where we start here with, again, all potential energy, but now watch the maximum speed when you get to the bottom. So before, once you got to the bottom, the speed stayed constant. But now we have friction continues to do work. Okay, so she's going off the screen, but she's continuing to slow down, right, wherever she is, off in the mountains somewhere, or the plains, the fields, whatever it is. But her speed is continuing to slow down. Her kinetic energy is continuing to decrease as friction does more and more work on her skateboard. Right, so we need to figure out, and in this case, we already know the definition of work. It's just going to be the force of friction times the displacement of the object. And the thing to remember about friction is that friction always does negative work. Right? Friction always slows you down. Friction always removes energy from the system. However you define your system, work done by friction will always remove energy. Demo that reminds us a bit about centripetal motion using the freeform version, and that allows us to make the track whatever we want. So here we can look at the skater starting up here. It's higher than the top of the loop, so we might expect, well, whatever potential energy she has here is going to be greater than at the top of the loop, so she'll definitely have some kinetic energy and still be moving as she goes around. But as we watch this go in slow motion, right, so we can see the potential energy decreases as it gets to the bottom, greatest kinetic energy at the bottom. But then near the top, she flies off, right? And okay, she magically gets back on, but if that were a roller coaster, that would be really dangerous. Now we can see that just having some kinetic energy at the top of the loop is not enough. We need to have a situation where that velocity matches the centripetal acceleration that's required to go around the loop. So if we make the loop, we keep the top at the same height, but we make the loop a little bit tighter, right? So now we have a smaller radius. Now the centripetal acceleration should be high enough to allow her to go smoothly around the loop. Let's watch. All right, so here she makes it all the way around without losing contact. So this is a reminder that we, even as we think about kinetic energy, for certain situations, we still have to remember centripetal motion.
Your film is now ready to be shown.